Hello, everybody, and welcome to Diluted Gravity. Um, are more specifically incline plane problems, and that's where we're going to use diluted gravity. Is using these, blocks on ramps type of problems, or blocks on an incline plane. So far up into this unit, we've looked at force of friction and force of gravity, normal force, and these are the forces that we are going to see on this block on an incline plane. So let's start by looking at this block here, example 1. So there's a block on an incline plane, and we need to start by labeling the forces or doing our free body diagram. So let's start from the middle here, and I will say, okay, first of all, we always have force of gravity acting straight down. That's perfect. We also have normal force. Normal force is always perpendicular to the surface. So in this case, normal force is going to look something like that. And possibly, if there's friction on the ramp, we're going to be looking at both types of problems. We're going to be looking at problems with friction and without friction. So you just have to be careful. It's usually in the question. So if there was friction, it's opposing motion. So we know this block wants to slide down the ramp. So friction is going to oppose the motion. The problem, or not the problem, but the challenge with these questions is that we have forces at weird angles. So if I were to draw these forces over here on this graph, I've got an X, Y set up here. You can see that friction's at a weird angle and normal force is at a weird angle. And gravity is the only one that's acting in the X or Y direction, which makes our life a lot easier. So something that you can do with forces like this that are at weird angles is you can, so these vectors on angles can be broken into components. That's what I've written right there. And this is all two-dimensional kinematics works this way as well. And if you do physics 12, you'll see a lot of this. So what I mean by that is, let's zoom in on this purple one here. Let's say, for example, this is a velocity of a soccer ball that was kicked. So the soccer ball was kicked at an angle. We know it's going to gain some height, and it's also going to gain some horizontal distance. What you can do is you can break this vector into its x component and y component. So we're looking for an x component and y component. This has nothing to do with our problem at hand, but we will use this skill to solve that problem. So let's break this into components. You can see that if we were to draw a dotted line straight down from the tip of that, our velocity x would be here, and our velocity y would look something like that. And normally you definitely need to know the angle here, because then you can use trig. If we know, for example, that this is 35 meters per second, and we know the angle, then we can solve for Vx and Vy, and we'll talk a little bit more about that. So instead of having your purple, hang on. Instead of having your purple velocity vector, you can think of this in terms of just a Vx and a Vy, and now you've broken that vector into components. So we're not going to use it at an angle. We're going to use a portion of it in the y direction and a portion of it in the x direction. So hopefully that makes sense. And then our math becomes a lot easier. And that will require some trig, and we will do that trig, so don't even worry. All right, so let's get back to our problem. You can see here we have three forces. We have normal force, force of friction, and force of gravity. Right now we have two forces at weird angles. So that means we would have to break two forces down into components. And that's just too much work when there's an easier way to do it. So what we're going to do is, up until this point, we've been always doing things in the xy direction where y is vertical and x is horizontal. And that has made our life pretty easy. Everything's been moving horizontally or vertically, so it's not been that big of a deal. But in this case, you can see movement happens in this direction right here, right? All of our movements going to happen along the plane, right, along the ramp. So what we can do is we can take this XY plot. We have the power to set our positives and negatives. Remember, we talked about that? You have the power to make left positive or right positive as long as you're consistent. We also have the power to rotate this frame, this XY frame. So now what we're going to do is we are going to use X being along the plane and Y being kind of in the direction of the normal force or perpendicular to the plane. What this does is it's going to take this diagram right here, or these forces, and it's going to make them look like, let's go over here. So now, if you look at our ramp, the normal force is going to be straight up. The force of friction is going to be in the negative x direction, and our force of gravity is going to look like this. So it's the force of, so now we only have one force at a weird angle, one force to be broken into components. So what that can actually look like is, and it'll be a lot easier once we do the math. Oh, let's make that. That's annoying. It won't go black. Blue, black. There we go. So now what we can do is, instead of dealing with that force of gravity on a weird angle, let's zoom in here, we can break it into components. So we can break it into, let's get a new color here, green. We can break it into a force of gravity in the y direction and a force of gravity in the x direction. So as long as we know an angle, then we can use trig to figure that out. So now our diagram is going to look like force of friction, normal force, force of gravity in the y, and force of gravity in the x, where we know that actually, you know, the actual physics of it is this right here. But we're not going to use that. This is our actual force of gravity. Because now all of our forces are in our xy, and it's a lot easier to deal with. So let's do some math. I think it'll make a lot more sense when we do some math. Okay. Yeah, I think I was just going to draw here. Now we have normal force, force of friction, force of gravity y, force of gravity x. So we have to do a little bit of trigonometry, and this is where this 35 degrees is going to come into play. So let's actually do a problem, and we'll see what's going on here. If a 5 kilogram box is sliding down an inclined plane of 42 degrees, how fast is it accelerating? So we'll draw our picture. It's always going to be good to draw a picture. We know that the mass is 5 kilograms. And our forces are going to be normal force. There's no friction, so we just have gravity now. Let's do dark green. Force of gravity. So we will make our xy. X will be along the plane surface, and y will be perpendicular. So what we really need to do is break this force of gravity into two components. Fg of x, or sorry, that's Fg of y. I always just break them, say force of gravity in the y direction, force of gravity in the x direction. we also need to say, okay, well, sorry, I'm sliding the screen around like crazy. You're probably getting motion sick. Our inclined plane is 42 degrees. That is always a measure down at the bottom here, 42 degrees. And the really cool thing with the way that these shapes work out is if this is 42 degrees, it means that this angle right here in our triangle is also 42 degrees. So we can do some trig on this. This is our right angle right here. So that means our green FG is the hypotenuse. That means our FG of x is the opposite, and FG of y is the adjacent. And we know the angle is 42. So we know that sine of 42 is going to equal opposite, which is FG of x, over hypotenuse, which is force of gravity. We can do a little bit of algebra. We're trying to find FG of x. So we can multiply by FG, and that cancels. And what we get is force of gravity x is going to equal, the full force of gravity multiplied by sine 42. We know force of gravity, right? We know force of gravity is mg, right? Mass times gravity. So mg sine 42. We can do the same thing with our FGY. Maybe I'll do it right here. FGY is going to equal, well, FGY is an adjacent, and we want to use hypotenuse, so we can use the cos ratio. Cos 42 is going to be FGY over FG. And then I can multiply both sides by FG. And we see that if that cancels, we get, well, our FGY is going to be FG multiplied by cos of our angle, or our inclined plane. And we know FG is going to be, this is going to be m times g cos 42. So what you can say, or what you can do is say FG x is equal to mg sine theta, and FGY is equal to mg cos theta. Those are two formulas that you can use in this unit. Hopefully that made sense. So now I can redraw these forces as Fn FGY and FGX. And I can actually solve for those FGY and FGX. So FGX is going to be mass times gravity sine theta, which will be, mass is 5 kilograms, gravity is 9.81, and we're going to multiply that by sine of the angle of the incline, which is 42. Which is, I've got my calculator here, 5 times 9.81 multiplied by sine 42 gives me 32.8 newtons. So FGX is 32.8 newtons. FGY is mass times gravity cos theta, so that will be 5 kilograms multiplied by 9.81 meters per second squared multiplied by cos 42. And we can do the same thing, 5 multiplied by 9.81 multiplied by cos 42. And we get 36.5 newtons. So FGY is 36.5 newtons. Before we go any further, we know that the block isn't moving in this direction right here, right? The block doesn't move off the ramp or into the ramp. So there's no acceleration, which means that those forces need to be balanced. So if FGY is 36.5 newtons, we know normal force is also 36.5 newtons. And then just be aware that they're in opposite directions. So if you were to do math on any of them, you need to make one negative, most likely the FGY. So if those are balanced, the only unbalanced force we have is in the x direction. So what are they asking? How fast is it accelerating? Well, we know the only thing that we have for acceleration in our dynamics unit is F net is equal to ma. So if Fn and Fgy are balanced, and obviously there's no movement in the y direction, the only force in the x direction is Fgx. So the net force is equal to Fgx is equal to m times a. So to get acceleration by itself, because that's what we're looking for, we can divide by m on both sides. We get acceleration is equal to Fgx over mass. And we know Fgx is 32.8 newtons. We know mass is 5 kilograms. And we get an acceleration of 6.56 meters per second squared. So the block is accelerating down the ramp at a rate of 6.56 meters per second squared. Awesome. So that was without friction. Let's add some friction into it. Here we go. If a 3 kilogram box is on an inclined plane, we need an angle. Let's put an angle in there. Let's say 28 degrees. If a 3 kilogram box is on an inclined plane of 28 degrees, what coefficient of friction is needed between the two surfaces in order to keep the box from sliding down the ramp? All right. So let's draw our picture here. Let's go a tad bigger. So we know that we will have a normal force. In this case, we know we're going to have a force of friction as well, because it says what coefficient of friction is needed, and we have a force of gravity acting downward. That's exactly that's what's happening in the actual problem. But what we're going to do is split that force of gravity into components. So now the way that you can think of it is, let's draw it out here. We have normal force, we have force of friction, we will have force of gravity in the y, and force of gravity in the x. So if this is a ramp at 28 degrees, we can solve for some of these. Let's do Fgx first. We know Fgx is equal to mg sine theta, and Fgy is equal to mg cos theta. It's going to be important that you know where these come from using the triangle. I don't mind if you use them like this, but I really want you to be able to know that there's trigonometry happening there, right? And that our triangle is something like this. That angle matches that 28. The FGY is the adjacent side. The FGX is the opposite side. And that's a right angle triangle. And you can use trig to actually solve for that. So I don't mind if you use it, but I really want you to know where it comes from. All right, so we know the mass is 3 kilograms. So this is going to be 3 multiplied by 9.81 multiplied by sine of 28. And the FGY is going to be 3 multiplied by 9.81 multiplied by cos of 28. And we can solve for both of those. 3 multiplied by 9.81 sine 28 is 13.8 newtons. And the same thing, but with cos 28 is going to be 25.98, let's say 26 newtons. So that means this force here is 13.8 newtons. We know that FGY is 26 newtons. FGY and Fn should equal the same, so normal force should be 26 newtons as well. And now what we're going to do is, let's think about what's going on here. So we have a box on a ramp, and we're looking for the coefficient of friction, which is our mu. So we know that comes in our force of friction formula, mu multiplied by Fn. We know Fn, which is great. We're looking for mu, so we need a force of friction. We don't actually know force of friction, but the other thing we do know is that we're looking for high enough force of friction that will keep the box from sliding down the ramp. So if the box is not sliding down the ramp, it's not moving. And if it's not moving, its net force should be 0, right? It's not accelerating, it has no net force. Therefore, the force of friction has to equal, in order for the box to not accelerate, F, force of friction, has to equal force of gravity in the x, right? It has to be the same. So this has to be 13.8 newtons as well. So now I can take that formula and say Fgx is equal to mu multiplied by normal force. We can divide normal force from both sides, and we get mu is equal to Fgx over normal force. I just made this up, so hopefully it comes out to be a half-decent number. Fgx is going to be 13.8 newtons, and our normal force is 26 newtons. So we can go 13.8 divided by 26. So our mu value is 0.53. And we know that that is not, it doesn't have a unit. And that seems like a pretty good one, actually. If we wanted, we could go on Google and figure out what matches that, what material, and that's probably what our ramp is made out of. So there is a lot of like balancing forces, force of friction, normal force, things you've dealt with before. The weird thing is now we're taking our reference of xy and we're going to tilt it on its side and break that force of gravity into components. You can use those formulas as long as you know how to derive them as well. That's it for our dynamics unit. Thanks for watching. Don't forget to like and subscribe.